So we got to get into some basic statistics, and this is the animated portion of our lesson. For those of you who missed it, here we go again. Okay, so data worlds. We've got two types of data worlds. You've got the variable that you're studying, that's the y, or it could be the x. Inputs or outputs, it doesn't matter, they all get measured. Those fall into two major categories, discrete data and continuous data. I've said this before, I think, that if information was water, the manufacturing world is the rich Brazilian rainforest. The service world, the Gobi Desert. And the reason being is simply the type of data that you'll find. In the service world, you find a plethora of discrete data. A lot of it just simple count data. Male, female, types of cars in the parking lot, type of mistakes being made on the order form, types of clients coming in that we're serving. So it's still data and it's still relevant, but the problem is that it's not as rich. But the minute I go over into the Brazilian rainforest here, manufacturing, I'm now measuring width, I'm measuring weight, I'm measuring temperature, rainfall, pressure, all of those things, and each one of them could be stated to an infinite number of decimal places. I can have one mistake, I can have two mistakes, but I can't have 2.3 mistakes. However, if I'm measuring something like weight, I can go to a lot of decimal places. I can state it as a fraction. I can state it as a ratio even. So continuous data is measurement scale can be meaningfully divided into finer and finer increments. It's measured on a continuum, on a scale. It's much more robust for statistical analysis. So obviously, wherever possible, we want to be in the rich Brazilian rainforest. And then it's associated with things like length, weight, ratios, anything you can state to an infinite number of decimal places, or as a fraction, would fall within the continuous data world. The discrete data, the Gobi Desert, values can only vary by whole units, may or may not follow a specific order. Not very powerful for statistical analysis, but still can be analyzed statistically. And then finally, it would fall into classifications or counts or ratings. So obviously a survey would be a discrete type of data collection simply because you're ranking things from 1 to 5. So types of discrete data. So we go down a layer. If we're in the discrete data world, what kind of data are we looking at? There's two major categories. One is nominal data, which is the weakest of all. It's made up of values that can only be distinguished by name. Male, female, blue, green, orange, red. Types of infirmities or modalities or types of cases coming into the hospital. The reason that it's called nominal is because there's no logical order. I can put male, female, female, male, doesn't really matter. And then finally, we've come down to ordinal data. The only difference between ordinal and nominal data is ordinal, order. Ordinal data follows a specific order. So if you're doing a survey on a scale of 1 to 5, there is a logical order. You don't go from 1 to 5. You have to go 1, 2, 3, 4, 5. And that's one piece of information that nominal data doesn't have. Nominal data doesn't care of the order, but I can leverage the knowledge of the order in my analysis now when I'm analyzing ordinal data. So it's one more piece of information that allows me to have richer analysis, that's all. Interval data, so continuous world, interval data. It's ordered, it's a constant scale, there's no natural zero. So of course you can go negative, you can go positive. So temperature would be a perfect example of that as well. Differences make sense, but ratios do not. For example, 30 degrees minus 20 degrees is equal to 20 minus 10, but 20 divided by 10 doesn't mean that 20 degrees is twice as hot. That's just kind of the analogy for it that makes sense. Temperature, cold versus hot, dates, etc. Ratio data, ordered, has a constant scale, does have a natural zero, height, weight, age, length. I can't be negative so many pounds. I can't be negative so many inches. I start at 0 and I get taller.
So, real life question would be, so say the equation percentage of calls transferred, right?
Yeah.
Would you call that ordinal data, or would you call that ratio data?
Ratio data. Yeah, ratio
Because
data.
the underlying though is I transferred or I didn't transfer, right?
Yeah, but what you've done there, and very astute, Ian, is you've converted discrete data into continuous data. And that's one of our goals, is that if I'm in the discrete world of call abandon rates, right? When I abandon a call in a call center, if I count the number of people that have hung up before we've answered the call, that would be discrete data. But if I now divide that into the total number of calls handled, it becomes a percentage. What I've physically done is I've gone from the Gobi Desert into the rich Brazilian rainforest. And I'm always trying to do that. So now with that count data, I could simply put on a run chart the number of people that have abandoned a call each day, right? And that would show me the variation around that. But I could take that same data and state it as a percentage and put it in a proportion chart, which is a control chart, with a plus and minus 3 standard deviation. Why? Because those proportions are normally distributed and follow the normal probability model, where if I go more than 3 standard deviation away from the average of what the proportion was for the whole, I now know that Dorothy ain't in Kansas anymore. That's an unusual day. And so we'll see proportion charts when we start using control charts. So that is a good trick that you want to do, is wherever possible, how do we get into the rich Brazilian rainforest? Because those tests and cars that are sitting in that parking lot over there for me to do analysis are richer and stronger and don't require as much fuel for me to be able to make an analysis. So we have dealt a little bit around populations and samples and the reason why we do statistics. We've dealt with descriptive statistics as well as inferential statistics in our early studies. We haven't really dived into it, but we've done it. Descriptive statistics are about studying the behavior of the sample. Inferential statistics is to learn something about the population by exploring the behavior of the sample. So we're inferring what we see in the sample back on the population, knowing that during that inference, what we see is not necessarily exactly what the population is doing. It's an estimate of what we think the population is doing. And around that estimate will always be some form of error. And I need to understand what that error may be. Another way of looking at that, how big of a difference do I need to see before I can say that the difference that I'm seeing is real in the population? That's what we really are trying to understand when we're looking at things like confidence intervals, our estimates around where we think the true population value resides. So populations and samples, a population is every possible observation, but it's rare to capture all of that information. So there could be a number of reasons. It could be cost, time, just doesn't make sense in terms of being able to do it. It could be destructive in nature. I mean, sometimes when we test for things in manufacturing, we're actually breaking it. Well, I'm not going to drive all of the Volvos into the wall or drop them on their hood. I'll only drop a sample because it costs a lot of money. You know, so destructive testing would be one of the reasons why we sample as well. So what we do with the sample, and we've already dealt with some of the symbols. We have the little U with the kind of a tail on it, which is called mu, is a Greek symbol, and that it represents the population average. When we take a sample from the population and calculate the sample average, that sample average is called X bar. The sample average is an estimate of what the true population average is, but our estimate will always have a small margin of error. In statistics, we want to know how big that possible error might be, because it will affect my ability to make a decision. How big of a difference do you need to see before you're willing to say, hey, something's changed in the population? My sample says the population has changed. Really, that's the crux of when we're doing these types of statistics. So we're dealing with a lot of numbers. And we want to be able to describe what it is we're seeing, right? Descriptive statistics. From that, we were able to get insights or knowledge or wisdom, and later on we're able to test hypotheses. So the first thing we want to do is when we get data from a system or a process, it's like going to Niagara Falls for the first time and just taking a picture. What is it that I'm seeing? What does it look like at that moment in time? And just because the falls look that way when I take that snapshot, does that mean when I come back a week later, it's going to look exactly the same? Probably not. So that's the difference between the sample and what the population is actually doing. Right? The sample gives me an estimate, and from that I might make a prediction, but the question is how much off might I be in my assumption around the population value.